So let's do one more of these. Let's find all complex numbered solutions to the equation z to the seventh equals 3 over root 2 plus 3 over root 2i. The thing to recognize is that this is really the same thing as, as being asked to find all the seventh roots of the complex number that's given, because recall that an nth root is defined as a number such that when we raise it to the nth power, we get the original number back. So I'm asking what all numbers z that I can find are, so that when I raise them to the seventh power, I get 3 over root 2 plus 3 over root 2i. So the first thing to do is we want to show where this number 3 over root 2 plus 3 over root 2i exists on the complex plane. It's going to exist right here. So if this is 3 over root 2 on the real axis and 3 over root 2 on the imaginary axis, then we can see that the number using the distance formula, that's going to be a radius of square root of 9 over 2 plus 9 over 2. I'm just squaring the 3 over root 2, and that gives us the square root of 9, or 3. So the radius of this number is 3, and we can see that its angle theta is going to be arctangent of 3 over root 2 over 3 over root 2. Isn't that surprising? It's going to be arctangent of 1, which is pi over 4. I know that in the earlier examples I just said let's just sort of eyeball the angle, because I'm always going to give you an angle that's one of the unit circle angles that you know, but this is technically how you would find it using the arctangent function. So we have that this equation actually reduces to z to the seventh equals 3 e to the I pi over 4. So we can actually just find the first root just using what we already know about finding seventh roots. In other words, I'm just going to raise both sides of this equation to the power 1/7, and that'll give me z equals 3e to the I pi over 4 to the 1/7 power. Well, look at that. That's going to do the exact same thing that we did sort of by that bullet list instruction in the previous problem. We're going to get 3 to the 1/7 times, when I nest exponents, I simply multiply the exponents together, so that's going to be e to the I. Pi over 4 times 1/7 is pi over 28. So this is equal to the first of the seventh roots. So now we just have to find the other ones. Let's find the angle between them. The roots are all going to be 1/7 of the way around the circle. That's how it works. There are 7 roots. They're 1/7 of the way around the circle from each other. One circle is 2 pi. A seventh of one circle is 2 pi over 7. Notice that we have a denominator of 28, so it's going to be a little more convenient for me to add these angles in. If I convert this into 8 pi over 28, I just multiplied the top and bottom by 4. So the rest of the roots, so I have the first of the roots, that's one of them. The second through seventh roots are, I'm just going to list them all. 3 to the 1/7, call it the same radius for each root, times e to the I. Pi over 28 is going to be, let's see, I've got pi over 28, and I have to add 8 pi over 28, so that's going to be 9 pi over 28. Next root is 3 to the 1/7, e to the I. 9 and 8 is 17, so that's 17 pi over 28. 3 to the 1/7 times e to the I. 25 pi over 28. 3 to the 1/7, e to the I. 33 pi over 28. 2, 3, 4, 5. I've got 2 more to do. 3 to the 1/7, e to the I. 33 and 8 is 41. And then 3 to the 1/7 times e to the I. 49 pi over 28. And just checking, it's 57. So yeah, okay. So there we go. Okay, so this is, let's just label these. This is the second, third, the fourth, the fifth, the sixth, and the seventh. And up here, of course, I've got the first. And note that these are all seventh roots of the number that was given. It's just that this is the first of the seventh roots. This is the second of the seventh roots. This is the third of the seventh roots. I'm not trying to say that this is a second root or square root. This is a third root, fourth root, fifth root. I'm saying that they're all seventh roots, and this is the ordinal number of each of them. So let's put a box around this. The two things that collectively have boxes around them are the answer to this. You have to find all the all of the solutions to this equation. There are 7 such solutions. There's that one, and then plus these 6 are also solutions to that equation. And if you want to verify that any of these is a solution to that equation, just pick any one of these, like let's say this one, and raise it to the 7th power, and see if you get this number back. If you do, then you found a 7th root of that number. By the way, I had mentioned that we'd see why it is that there are 2 square roots of -1. It's because by this algorithm, there are always going to be 2 square roots. Think about this. How many square roots are there of the number 4? Well, there are 2, plus and minus 2, and look where they are. We take the positive numeric square root of 4, which is 2, thereby giving us a circle of radius 2, and the 2 roots are all on the circle of radius 2, exactly halfway around the circle from each other. Positive 2 and -2. Going back to square root of -1, think about how we would find the square root of -1. We put -1 there. This is an angle. This is e to the I pi. We cut the angle in half, which gives us the square root of -1, which is right there. And the 2 square roots of -1 are exactly halfway around the unit circle. There are 2 second roots of any number. They're all exactly 1/2 of a circle around from each other. So we find one of them by the algorithm, and then we simply add whatever fraction of the circle until we have found all the roots. So there we go. That's how we find the n nth roots of a number, or equivalently, all the solutions to the equation z to the n equals some number.